My name is Leng. I'm from Los Alamos National Lab. So today my talk is titled Arbitrary Order Virtual Element Method for High Order Phase Field Modeling of Dynamic Fracture. A little background of this project: about a year ago, we wanted to do using VEM for the phase field fracture modeling, but our in-house code is too slow. So we were looking for some platform MFEM package that can do parallelization. That's the main motivation we implement VEM in MFEM. So this is the outline of my presentation. I'll start with the motivation and introduce the high order phase field fracture. Then I'll spend the majority of my time talking about virtual element method. Virtual element method is a finite element method. So the assembly procedure is the same as the classical finite element method. Then I'll discuss some numerical example about dynamic crack branching and also the quasi-static benchmark test. I'll end my presentation with the summary. Motivation: dynamic fracture is an important consideration in many problems, such as the one shown on the left. What you see is a snapshot of a high-speed camera which catch the hemispherical metallic shell explode. What in there? The hemispherical has a high pressure inside. When the pressure goes off, the shell would explode, and what you see is the so-called cornflake pattern of these pieces. Dynamic fracture is also important in many applications, shown on the second figure, which shows a steel ball traveling at high speed, penetrating the steel plate. The physical process that cultivate dynamic fracture are complex. It depends on the material at hand and also the applied loading, but we do not have the capability to predict this process. In terms of modeling material failure, there is a famous quote in this review paper. Predictive modeling of crack initiation and propagation in materials and structures remains one of the most significant challenges in solid mechanics. There are two general approaches to represent material failure. One is the discrete approach, which represents failure or fracture as a discontinuity. Another approach is the continuous approach or diffuse approach, which uses a damage variable to represent failure. The examples of the discrete approach include embedded finite element XFEM or GFEM, and the examples of continuous approach include continuous damage mechanics, pair dynamics, and phase field fracture. In terms of modeling fracture, the figure on the left shows the sharp crack. We have a crack gamma C in this body omega 0. The energy of this system consists of two parts. The first part is the elastic energy. The second part is the fracture energy. The fracture energy is the codimensional one surface integral. So in phase field method, we use volume integral, shown on the bottom right, to approximate this volume integral. As this length scale goes to 0, this energy on the bottom left will gamma converge to the energy on the left, which is a sharp crack representation. And this is the beauty of phase field method for fractures. If we minimize this energy, we arrive at the strong form or the phase field fracture model. I will not talk about why we choose the high order phase field model, because that's not the main focus here at this workshop. So we have two equations. The first one is the elastodynamics equation. The second one is the high order phase field equation. We have a fourth order derivative. So the classical finite element will have some problem, but we can do that. We can use IGA. That's the famous for IGA has higher order continuity. But in VEM, I want to show you we can also do this. to use the C1 element. And now is the motivation. Why do we want to use polytopal elements? If we use polytopal elements, which can significantly reduce the meshing difficulty, which the figure on the top right show is a figure we took from Virtual Cross. That's a software developed by Sandia National Lab. So by using polytopal elements, we can avoid using overly stiff triangular or tetrahedral elements. This is important if you want to. This is especially important for explicit time stepping. So we can use a larger time step. Another motivation to use polytopal elements is we can respect the microstructure of the materials. There are two figures. The bottom left shows the microstructure of copper. It has each grain. It has grain. The grains are of polytopal shape. They are weird. They can be convex. They can be non-convex. And each grain, they're at the atomic level. Their lattices are different. So that their response to their mechanical response to loading is different. So our goal is to use each element to represent each grain. Another application is the figure on the right, which is the adipose tissue. If folks are doing biomechanics, this is our fat tissue. The white polygons are each adipocyte. In 2D, they look like polygon. And the darker color, they are fibers. So their mechanical response are also different. So those are the motivation. Now, before I introduce VEM, I want to go back to grad school and briefly introduce finite element. So we solved the diffusion equation. For simplicity, we just assume homogeneous boundary condition. This toy problem can be recast into the variational form. So we seek a solution of U in H01 that satisfies this variational equation. Using Galerkian approximation, we find UH in this finite dimensional space V0HK, which is the subspace in H01. So this variation of formulation is satisfied. Then next we introduce basis function, and we express UH in terms using this basis function. Get a linear form, solve this a linear system, we get our solution. What I want to say here is a virtual element method follows the same procedure. VEM, it is a finite element method. Now is how to build basis function. In classical finite element, we know how to build a polynomial basis function up to order k explicitly on simple geometries like the triangle and quadrilateral in 2D, and also same applies for 3D simple geometries. Can we do the same for polygons? Can we build basis function on polygon explicitly? This question has been studied decades ago by this person, Eugene Watts, and his conclusion is that Lagrangian basis functions are not polynomials. So he proposed to use a rational basis function, and he wrote a book which came out in 1975, and another version came out recently, 2016. So we cannot build polynomial basis function or we cannot build Lagrangian basis functions on this polygon. Another way is to directly solve the local elliptic PDE on each element. It's called harmonic lifting. This is very expensive. So because you have to solve this Laplacian problem on each element to find the basis function. So in VEM, Franco Brazzi came up with this idea. We do not evaluate the basis function. We approximate them by using polynomial projections. So here are the three concepts of VEM. First of all, again, VEM is a finite element method. It has you use functional spaces and variational formulation. It has rigorous convergence analysis and error estimate. we build local stiffness spaces, local stiffness matrix, and distribute to global stiffness matrix. So the same procedure as what we do in finite element method. The finite element space in the virtual element method is virtual. That's why they call it virtual element method. We do not compute the basis function. We do not need to know the basis function. We can just use their polynomial projections. The last concept is we can choose the degrees of freedom wisely so that we can compute the polynomial projection without any approximation. Now here I'll introduce the conforming virtual element space. The UH is a function of H1 and it is continuous on the boundary. And the second condition, the Laplacian of VH is in polynomial of k minus 1. This result is a little bit old. There are newer results. The last one, that's also very important. The function VH is restrict on the boundary on each edge, or say in this polygon, is a polynomial. It lives in the polynomial space of order k. We will use it later. When we do like integration on the boundary, that's very important. Then this is the degrees of freedom. Say that the first one for k equals 1, we only need degrees of freedom on the vertices. For k equals 2, we need degrees of freedom on the edge and also internal. And by choosing these degrees of freedom, it is proof that they can, the solution exists. It's well posed, this discrete problem. And the polynomial space of polynomials of degree up to k is a subspace of this virtual element space, VKH.
Are those normal degrees of freedom values at this point?
You mean that circles?
Any of them?
Yes. Like the k equals 1, the green circles are nodal degrees of freedom.
And the red square is a value at the midpoint of it?
It can be, you can also be the moment, an integral type, also the internal. And the last concept, that the elliptic projection operator is computable. I will revisit what computable means by choosing this virtual element space. So now this is the meaning of virtual element method, the elliptic projector pi k numpna. It is defined, pi k numpna projects a function VH in the virtual element space to the polynomial space. It is defined in this as inner product that induces the H1 semi-norm. Of course, this is only defined up to a constant. We can fix the constant using this two equation shown in the middle of the slide. The breakthrough here is that we can always choose the degrees of freedom so that the elliptic projection is computable. This pi k numpna is computable. If you look at the bottom equation of this slide, this is the definition of pi k numpna. On the left-hand side, the projection of VH is a polynomial. So the left-hand side is computable. On the right-hand side, we don't know what is VH. So how can we compute it? So we do integration by parts. Then disassemble this part into two parts, an integral inside the element and also the surface integral, or the boundary integral. The boundary integral, the first term in the bracket is the polynomial. We know how to compute it. VH, we don't know what is VH, but VH is restrict to the boundary is a polynomial. So the second term, we have no problem computing it. For the first term, here, Laplacian of Q multiplied by VH, for k equals 1, we don't have this term, it's literally 0. But for k equals 2, we don't know what it is. That's why we define it as the degrees of freedom. For k equals 1, Laplacian of Q is a constant. That's why in this slide for k equals 2, we have a degree of freedom inside of the element. Okay, now we know how to calculate how to compute the polynomial projection. We do a useful decomposition of the basis function. We call it canonical basis function because we have another basis function for polynomial basis function. And this virtual element basis function satisfy the Conacher delta property. And we decompose it into two parts. The first part is the polynomial projection. The second part is the complement. We know how to compute the polynomial projection, but we don't know how to compute the complement. But when we assemble the stiffness matrix, we have the we need this term where the pi k number phi I multiplied by the complement of this projection. It is 0 by definition in this inner product that induces H1 semi-norm. Okay, now let's look at how to assemble the local stiffness matrix. By using this projection, we have 4 terms. The mixed terms are 0, as I introduced in the previous slide. It's by definition. Then we are left with 2 terms. The first term is a polynomial projection multiplied by polynomial projection. It is computable. And the complement multiplied by complement, we don't know how to compute it. But what we do, we approximate it. This is also called the stabilization term. It is proved that as long as this approximation satisfies this condition, it is any continuous bilinear form. It is symmetric and positive definite on the kernel of the pi k number. And it is computable using the degrees of freedom. So then we have no problem of approximation in this term. Now we know how to do the local stiffness matrix. Then we can just loop through each element and distribute the local stiffness matrix to the global stiffness matrix. And another slide is based on the assumption of the regularity of the solution and the mesh, we have rigorous convergence results. The traditional or the classical convergence results in finite element. This slide, now let's go back to the high order physics field fracture model. We still need to solve the equation. This slide I've shown earlier, this is the degrees freedom we choose for the displacement. This is the classical or the traditional VEM. For high H2, for the high order, because we have fourth order derivative, we need H2 conforming or C1 continuous element. So we need to constrain the derivative. The minimal polynomial degree is k equals 2. And for k equals 3, we need to constrain the normal direction as well. For k equals 3, we need the degrees of freedom on the edge. So we implement the VEM into MFEM. Here I just introduced 4 mesh. We use the first column is the mesh I generate using, say, GFEM, a triangular mesh and also a quadrilateral mesh. You can use any software. Then we connect the bar center of those meshes and generate the dual mesh, which is shown in the middle. Down you can see a lot of polygons there, and the dual relationship are shown on the right column. And here you can see we have elements of size like 5 all the way to 9 or 3, and the middle one is concave. It is not convex. That's also what VEM can do. Let's look at some interesting problem, the double cantilever beam. So we have a beam, we pull the top and bottom side. Depending on the load, we put the load, we increase the load linearly until it reaches the plateau. Depending on the magnitude of this load, we can get a single crack branching event or multiple crack branching event. Here are the results. The mesh is shown on the left. We have almost 0.7 million elements. The top video shows we have only single crack branching event, and the bottom on the right shows we have multiple crack branching event. Again, In this slide, we just show we use the 4 elements or 4 meshes I introduced earlier. The top row shows we only have triangle. The second row is the dual of the triangle. We have more polygons. And the third row is the quadrilateral. The last row is the dual of the quadrilateral. In this mesh, there are more quadrilateral elements than polygons. And each column corresponds to the same time step. So what you can see is the pattern, the crack patterns are similar for all the meshes, but at the details they are different. Especially where I have the white arrow, the detail is the crack branching. So on the left, you can see either there are 2 branches, either the top one or the bottom one will dominate the crack branching event. Now let's move to the quasi-static tensile test. We have a square plate, a pre-notched square plate. We fix the bottom and just pull the top side. The mesh is shown here. Again, we compare different elements. Each row corresponds to the same loading step, and each column corresponds to the same mesh. And what we found interesting is for the triangular mesh, the crack has propagated further compared to the other mesh. We believe this is because the triangular mesh is overly stiff. So this concludes, here's a summary of my presentation. We developed a virtual element framework in MFEM to solve the dynamic fracture problems governed by high-order phase field fracture model on polytopal meshes. And we verified our framework using benchmark tests and also dynamic fracture. What come out from this project, this paper that just got published this month. And what I want to show here is in the code, what's different. This is example 1. What's the only different is how to define the H1. This is finite element connection, but I defined a VEM collection. So that's the only difference from a user perspective. This concludes my presentation. I can take questions if you have any.